today's lecture, we will talk about nuclear spectra. Let's start our lecture with a new energy spectra. So you know that many different reactions may occur during collisions between the two nuclear particles. I mean, if you remember last time in last lecture, we discussed about nuclear reactions, and I told you that it's mainly interactions between the two particles or the two nuclei. So here we are saying that many different reactions may occur during collisions between the two nuclear particles. So you know that when there is a collision, so the question is normally about the question is normally that whether the collision is elastic or inelastic. So as a result of that collisions, we have scatterings, and again, so we are having the same question in minds, whether the scattering is elastic or inelastic. So in elastic and inelastic scatterings, the incoming and the outgoing particles are same. As for example, you can see these particular reactions, that is these are the incoming particles, that is the capital A is basically representing the target nucleus, while the small a is representing the incident particle. So we're saying that it's a elastic scattering. So according to our definitions, we're saying that the incoming and the outgoing particles, they are the same in elastic scatterings. But if we are saying that the collision is anelastic, so in anelastic scattering, you say the outgoing an outgoing particle is one of the particles. It goes into an excited state. I mean, the static signs, particularly here, represents that in anelastic scattering, one of the nuclei that is that we indicated with the static signs is basically and the excited channels. So in nuclear reactions, the exit channels will have more than two particles, just like you can see in this particular reactions. I mean, in the reactions, we have two particles. We have an incident particle that will be represented by small alphabet A, and the target nucleus or target nuclei that will be represented by A. So as a result of that nuclear reactions, we have more than two particles. So one is the heavier nucleus, and the others are the ejected particles. So according to the natures, as we discussed earlier in the previous lectures, according to the nature and energy of the reactions, we can classify them. I mean, we have to have clear look on the energy and the natures of the reactions. According to that, we can classify any nuclear reaction. So the most important classes of nuclear reactions are compound nuclear reactions and direct nuclear reactions. Already we have the characterizations of nuclear reactions. Now we are saying that's how I mean we can classify them. I mean how we can classify the nuclear reactions. So there are two major categories in which we can classify the nuclear reactions. So the first category is compound nuclear reactions, and the second category is we have direct nuclear reactions. So direct nuclear reactions occurs during a brief period of time, a brief period of contact between the colliding particles and peripheral collisions. These reactions are usually a single step process. I mean, they're not occurring as a lengthy scale. So let's have further details about direct nuclear reactions, that how these reactions occurs and what is the duration for these kind of reactions. So direct reactions occurs during a brief period of contact between the colliding particles and a peripheral collisions. I mean, this is somehow a short and precise definitions for the direct collision. So the projectile, you know that during the collisions or during nuclear reactions, we have one particle that we bombard on the target, and that particular particle we call the projectile. So when we fire the projectile and the target, so the projectile transfers energy or pickups or loses nucleons to the nucleus within a short time, and that short time is equal to 10 raised to power minus 21 second. I mean, the projectile that basically we fire on the target nucleus. So there are many out of the many possibilities we can have that the projectile can transfer its energy, or it can pack up energy, or loses nucleon to the nucleus, and all these things they can happen at a very short time intervals that we have mentioned here, and 10 raised to power minus 21 second. So energy and this short duration of time, the energy and momentum transfer are relatively small. So direct collision are particularly useful in experimental nuclear physics. Why it's important there? So it's because the reaction mechanisms are often simple enough to calculate the sufficient accuracy to probe the structure of the target nucleus. I mean, this is why we're saying there's importance in experimental nuclear physics, and the reasons we already it's given is that the mechanisms are often samples. That can be effectively used to calculate with sufficient accuracy to probe the structures of the target nucleus. So, what are the compounds and nuclear reactions? We briefly describe about the direct nuclear reactions. So what is the compound nuclear reactions? Uh, so, in a compound nuclear reactions, the projectile fuses with the target to form a compound nucleus. Just like the obvious meaning specified. So in this kind of reactions, we when we bombard a particle or we strike a projectile and the target, so what actually happens? The projectile is basically fuses with the target nucleus. This is the key concept for the compound nuclear reaction. So what happened later on? A compound nucleus later on emits one or more particles. The projectile first is combined with the target nucleus, and that combinations occurs and form a compound nucleus for some whiles. Then the compound nucleus, after some times, it emits one or more particles. So during the emissions, either a low energy projectile is observed. When we have the compound nuclear reactions, so in that compound nuclear reactions, either a low energy projectile is observed or a high energy particle transfer energy to the nucleus. These are the possibilities during compound nuclear reactions. So after that, it's leaving it with too much energy to be fully bound together. Let me explain again. In compound nuclear reactions, either a low energy projectile is observed. This is the possibility during a compound nuclear reaction. That is, we are saying that either a low energy projectile is observed or a high energy particles transfer energy to the nucleus, leaving it with too much energy to be fully bonded together. So on a time scales, if you measure, just like we have a time scale for direct nuclear reaction, so just like that, we have a time scales of about 10 raised to power minus 19 seconds. So particle remains together until enough energy happen to be concentrated and one nucleus to escape the mutual attractions. So this is the durations of time for which the nucleons they remain in compounds and a compound stays until it gets energy, and it's been escaped from that mutual interactions. So if we want to show graphically the reaction mechanism, so in that reaction mechanism, you can see it here. We have plotted the yields of reactions against the energy of the outgoing particle. So here you can see that for compound nuclear reactions, we can see here a continuum, a continuum for the compound nuclear reactions. But and this is basically happens is a low energy. We have the lowest energy, so we can have that continuum for the compound nuclear reactions. But if we move toward the higher energy, I mean the energy of outgoing particle, if we increase our, if we are going towards the high energy of the outgoing particle, so here you can see that we enter into direct nuclear reactions regions, and here you can see that the value yield of reaction values basically we have in discrete form. So again, you can visualize here that for inelastic scattering and transferring reactions, here you can see a discrete values, but these discrete values are very I mean it's not too big, it's smaller. And when we have the elastic scattering, so you can see that the higher energy we can get the elastic scatterings. So here the discrete values are comparably high as compared to the one that we have in inelastic scatterings and transferring reactions. So how we explain these reaction mechanism? So just like I mean, as we observe a number of discrete peaks representing the inelastic scattering, uh, analysis scattering and transferring reactions. I mean, it's here, I mean, you already observed there are few peaks for analysis scattering and transferring energy. At lower energy, the peaks are broadened because of the spread in energy of the incident particles. I mean, that you already observed on that particular graph, that low energy the peaks are broadened, and the reasons for that broadening of the peak is the spread and energy of the incident particle. I mean, when the incident particles strike the target, its energy spread. So just because of that spread and energy, we have peak they are being broadened. And again, as you observed on the previous slide, that at low energies there is a broad continuum, and this broad continuum is basically due to decay of compound nucleus. I mean, the broad continuums is basically the indications of the decaying of the compound nucleus, which we already described, that a compound nucleus only lasts for a durations that we specified on the previous slide in a time duration of 10 raised to power minus 19 seconds. So in a compound nuclear reactions, equilibrium is reached and the compound nucleus will lose its energy over a period of time by emitting the particles, mainly neutrons and protons. I mean, these are the possibilities that the particles which might be emitted during the I mean, so when the compound nucleus is decaying, so the probability for the emission of the particle is basically I mean, some neutrons or the proton. I mean, neutrons and protons are basically escape from the compound nucleus. So this is all we have for these lectures. See you on next lecture. Till then, bye bye.